Hello everyone. Today I'm going to be discussing the paper The Use of Likely Invariants as Feedback for Fuzzers, published at Unix Security in 2021. So first, let me start with a question to all of you. If a fuzzer reaches a line of code that's vulnerable to a crash, why might it still fail to trigger that crash? The answer is that a lot of modern fuzzers today are extremely good with maximizing code coverage. They explore programs by generating all kinds of different inputs that can cause new paths to be executed. This approach has found a countless number of vulnerabilities in real-world production software, but coverage alone doesn't guarantee that a bug will be triggered. Many vulnerabilities depend not just on reaching the right block of code, but also the program having a specific internal state. This paper explores a very fascinating idea. What if fuzzers could be guided not just by where the execution of the program goes, but also by how the internal program state behaves? The authors of this paper propose a model to incorporate this idea of state awareness into fuzzing feedback without causing that massive bottleneck that comes with tracing program state. So before we dive into the specifics of this paper, we first need to understand a few things about fuzzing. So to define it, fuzzing is a generally automated software testing technique that finds bugs in a program by executing it with mutated inputs. There are several different types of fuzzing that are important to know. We have black box fuzzers, which simply generate random inputs and observe crashes while having no actual visibility into the program's execution. On the other hand, we have white box fuzzers, which build a full picture of the program being executed. These are very, very powerful approaches. However, the paper does note that white box fuzzers are often computationally untenable. In the middle of these two strategies, we have gray box fuzzers, which are the most common approach seen with a lot of modern fuzzers such as AFL. These fuzzers access very lightweight information about a program and use it to generate better mutations. A common example of this is using code coverage, which we've seen. What this does is it creates evolution, where the inputs that explore new behaviors and paths are prioritized as interesting inputs. Commonly known as coverage-guided fuzzing, this process has proven to be extremely effective, but this only explores the control flow of the program and not its internal state. According to this paper, one of the key limitations of coverage-guided fuzzing is that the coverage only reflects control flow, and that it struggles to find crashes when reachability alone is not sufficient. Many vulnerabilities in a program rely not only on reaching a specific point, but also on specific relationships between the data values present. This paper illustrates this with an example from the libsnd file audio library, which is predominantly in C. So in this snippet here, the program iterates through a block of encoded audio data and writes decoded values into a buffer called samples. The loop condition is obviously based on block size, and inside the loop, the program writes to the samples array using an index called sample index. What's interesting here is that the paper notes many coverage-guided fuzzers can easily reach the vulnerable line of code and execute the loop normally. From a coverage perspective, every execution looks almost exactly the same because the same control flow edges are taken every time. However, the heap overflow bug here occurs only when certain internal values, such as the number of channels and computed sample index, interact in a way that causes writes to go beyond the allocated buffer. So, in other words, the bug being found depends on the program's internal state rather than reaching new control flow paths. And since coverage-guided fuzzers only reward inputs that trigger new edges in the control flow graph, they have very little incentive to explore different combinations of these internal values when the control flow doesn't change. And so as a result, the fuzzer may repeatedly execute the same line of vulnerable code without ever actually triggering the heap overflow. So at this point, you may ask, so if coverage can't capture the program state directly, then why don't we track program state? And so doing this introduces an issue referred to in the paper as state explosion. So a program state, what that is it includes the values of variables, heap structures, memory contents, and more. And even small programs can have an astronomically large number of possible states. So, for example, consider a basic program that only has 10 32-bit integer values. That means that this program, since an integer can have 32 possible values here, it will have 2 to the 32nd to the 10th possible states, or 2 to the 320th. So if a fuzzer tries to treat every small change as a new state, it would quickly accumulate millions of inputs that are nearly identical to each other. And so as a result of this, the queue of saved inputs would explode, our performance would be degraded, and the search process would be just unfocused. So the challenge that's presented here is to incorporate the notion of program state without tracking the entire state. And so this paper proposes an elegant solution to this using something called invariants. So what is an invariant? An invariant is a property that holds at some point in a program's execution. So for example, in a normal loop, we might have an invariant such as 0 is less than or equal to I, less than or equal to n. Other examples can occur in things like conditional statements, so something like buffer size greater than 0. Invariants describe expected relationships between variables when execution reaches a certain location in a program. And so the authors introduce a concept they call likely invariants, which are discovered by analyzing trends in the program. So the system runs the program on a corpus and observes the values of variables at different basic blocks. And so if a property consistently holds across these executions, it's referred to as a likely invariant. For example, so if we observe values of A and B across 1,000 executions and observe that A is always less than B, then A less than B is a likely invariant. Now, these invariants are not guaranteed to hold, hence the name, so we could have a situation where A is not less than B. They simply represent a common pattern that has been observed in previous executions. However, we can use this fact to our advantage. So if an execution violates a likely invariant, so like from the example, if A is greater than B, it means that a program has entered an unusual or previously unexplored state. So now we get to the core idea of the entire paper, right, which is invariant-based fuzzing. So, let's take a look at how it actually works. So to start, the system begins by running a standard coverage-guided fuzzer once to collect the initial corpus of inputs. Using this corpus, it mines invariants to learn what the most likely invariants are at each basic block. And then these invariants can be used to gain insight into typical program state observed at those specific locations. During the fuzzing process, the program is instrumented to check whether or not these invariants hold. So if execution reaches a block and one of its invariants is violated, the system encodes that violation into the coverage feedback, which prioritizes this new violation in the generation of its inputs. It works the same way that an input that increases code coverage would cause the fuzzer to prioritize that input as interesting, as we've seen previously. So the key insight here is that the same control flow edge, combined with different invariants, is treated as new code coverage. Or in other words, even if control flow remains identical, a different internal state can appear as brand new behavior to the fuzzer. Doing this effectively partitions the state space into meaningful regions, so that instead of tracking the full program state, the system tracks which partitions, defined by the likely invariants, have been explored. Something to note here is that the implementation described in the paper uses the DICON likely invariant system and instruments the program with LLVM to check invariant violations during fuzzing. So it's actually very similar to the LLVM instrumentation that we've used earlier in the course to observe code coverage. So obviously, one important concern is whether adding this invariant feedback will lead to the state explosion like we discussed earlier. So the careful approach that the authors take to prevent this from happening is to control the number and the type of different invariants used. They talk about 3 different categories of invariants that they target so that they can discard them. The first category removes invariants that are impossible to violate. The authors detect these using using a technique called value range analysis, which determines whether a variable can ever take values that would break the invariant. The second category removes invariants that involve variables that are not meaningfully related to each other. This is done using something called comparability sets, which help identify variables that should not logically be compared to one another. And then finally, the system optimizes cases where multiple invariants share overlapping conditions, allowing them to reuse previously computed values instead of checking each invariant independently. So by filtering and optimizing invariants in these ways, the system keeps the number of checks manageable. This allows the fuzzer to explore more meaningful state partitions without causing the input queue or runtime overhead to explode. So going back to this example, now that we understand this new approach, let's take a look at where we've exposed that heap overflow error that went undetected when using coverage-guided fuzzing. When the authors analyzed executions of this code using their invariant mining approach, they observed patterns in the program state. So for example, conditions such as a PMS array of block size having a fixed expected value, which they note as 256 here, and then the loop index, block index, staying within those expected bounds. So these patterns become our likely invariants. They describe typical state observed when the execution reaches this code. However, the heap overflow error only happens when execution enters a state that violates those expectations. So for example, like unusual relationships between variables such as the block size and sample index. Again, from a control flow perspective, nothing changes. The same loop executes and the same edges are taken every time. But when looking at program state, execution has entered a new and unusual region. Because the invariant-based fuzzer treats invariant violations as new feedback, it rewards the inputs that cause them. Right? And so this encourages the fuzzer to continue to explore these regions of state space, which eventually produces inputs that trigger the heap overflow error. So even though coverage alone could reach this code, invariant feedback allows the fuzzer to distinguish between normal executions and the unusual states that directly expose the vulnerability. So taking a look at the author's results of this evaluation, it's clear that this approach has significant impact. So in their default configuration, the invariant guided fuzzer discovered 156% more bugs compared to a standard coverage-guided fuzzer. So in other words, it found nearly 2.5 times as many bugs under the same experimental conditions of 5 48-hour trials. The system also explored around 3.4 times more distinct invariant violations, suggesting that the system explores a much larger portion of the program's the program's state. What's also interesting here is that many of these bugs were not the same ones found by the traditional coverage-guided fuzzer, as we can see here by Figure 3. The paper shows that invariant-guided fuzzing discovers different vulnerabilities, meaning that it explores regions of the program that coverage alone does not prioritize. One result that I found to be personally surprising when reading this paper was how the choice of seed corpus can affect invariant learning. You might expect that using clean, valid input files would produce the best invariants, but the authors actually found the opposite. When invariants were learned only from valid files, the system discovered about 20% fewer bugs compared to learning invariants from the queue generated by an initial fuzzing run. Looking back, in hindsight, it makes sense. The fuzzer's queue has already pushed the program into a more unusual and diverse state, so the invariants learned from it capture a richer view of the program's behavior. Something really important to note also is that all of these improvements came with modest overhead only. Execution time only increased by about 8%, and the growth of the queue was manageable, around 62%, and did not suffer from state explosion. These results indicate that incorporating curated state information can meaningfully improve the effectiveness of fuzz testing. Despite all of the successes of this approach, however, it doesn't come without limitations. The first of which is that invariant mining is done during the initial phase. So this means that if new patterns are discovered during execution, they're not incorporated into the pool of invariants later on. Another limitation is that when indexing the shared map for coverage updates, there may be hash collisions, although it is important to note that this is a problem many AFL fuzzers have. Finally, the quality of learned invariants depends heavily on the initial seed corpus. This is something, however, that's also true for a lot of learning-based systems. While these limitations are considered, this approach does manage to balance state awareness and scalability without facing state explosion or intense overhead, which make it very viable. This paper brings to light an important step towards more state-aware fuzzing. Now, traditional fuzzing techniques that primarily focus on control flow use coverage to guide exploration. What this paper demonstrates is that incorporating very lightweight information about program state can significantly improve not only the number of bugs that are discovered, but also the quality of bugs found. Instead of attempting to track the entire program state, which we've seen is not reasonable, it would lead to state explosion, the authors use likely invariants to capture meaningful behavioral differences at specific points in the execution of a program. By combining coverage with invariant feedback, fuzzers can explore deeper regions of the program state space. My biggest takeaway after reading this paper was that coverage tells you where a program is supposed to go, but invariants tell you what it's doing when it gets there from the snapshot of the state that we get. When your fuzzer runs out of new paths to explore, I realized that the answer all the time isn't more coverage. It's looking deeper at the states hiding along the paths that you've already found, which was evident from the code snippet earlier on. Well, that's the end of my presentation. Thank you all for your time, and please don't hesitate to let me know if you have any questions.